Hey everyone, Mr. Fransky here. Today we're going to be talking about making integration by parts a little bit more bearable, or use what's called the tabular method, or just integration by parts using a table. So today we're going to be able to integrate using a table on polynomial problems. Let's take a look. So indefinite integral, stuff we've been talking about before, antiderivative, integration by parts, table method, all things that we've seen. Well, table method's going to be new, right? But let's see what's going on. So we have an annoying integral to start with. We actually did this one in class together, and let's kind of see why it's a problem. So if we think about our limit, so first of all, u sub is not going to work on this, because if u is e to the x, then du would have to be e to the x, and if u is x squared, I would need a 2x. Like, there's nothing here that is nice to be able to use u substitution. So I'm going straight to integration by parts. So I try limit, no logs, no inverse trig. There's a polynomial, it's x squared. The reason it's third on the list is because we've seen this before, right? So if u is x squared, then du is 2x dx, and dv then is e to the x. That means that e to the x dx, that means v is still e to the x, doesn't change at all. So now if we do our integration by parts, so uv is x squared e to the x minus integral v du. V du is going to be 2x e to the x dx. Okay, I'm going to rewrite that a little better. 2x e to the x. There we go. No, so 2x dx, excuse me. Okay, so now, this 2x e to the x, I'm going to take that 2 out, so I'm going to use a little bit of whiteboard magic here, put that 2 to the front. And so x e to the x is, we have to use parts again, right? So we're doing parts again. So I'm going to have x squared e to the x. I'm going to use my u and dv here. So u is going to be x now, because limit, once again, polynomial is my best option. So then du is just dx, so finally it goes away. And then dv is everything else, so it's e to the x dx. And that means v is e to the x. Okay. So x squared e to the x, that's still out here, minus 2 times, so big parentheses there. So we're going to have uv, x e to the x, minus integral v du. So v du is going to be just e to the x dx now. Right, because our derivative now got rid of the x. That equal sign looks kind of like an x, though. There we go. Okay. So now we can do that. So this is x squared e to the x minus 2x e to the x. And the antiderivative of e to the x is just e to the x, so I'm going to have negative times negative is a positive 2 e to the x. And then, of course, at the end, we just have to have a plus c somewhere. So there it is. Okay. So really not that cumbersome, but this idea of doing it twice is not fun. And gosh, what if this was like a fourth power? Right here, first derivative, or your first time you do it would have a cube, second time you do it would have a square, then a linear, and then finally it would be gone. You have to do this 4 times. It's a big pain. So the question is there some better way to do this? Well, let's take a look at what's going on here, right? So first of all, let's look at the x's. So right here, we have x squared, right? And then on the next part, it's just x. And then the next part, it's gone. Right, so we have an x squared, and that's actually a 2x, and then a 2. Interesting. So let's think about how x squared and 2x and 2 are related. And then the e to the x just kind of sticks around. So we have e to the x, so that just stays as an e to the x, and that just stays an e to the x. But what's happening here is the x squared, we keep taking the derivative, right? Because the first time u was x squared, so du is 2x dx. And then 2x was our u, so our x was our u, so our du is just dx. But we kept taking the derivative of that piece. The e to the x was our dv, so we anti-derived that, and that kept an e to the x, so we anti-derived it one more time, that gave us e to the x again. So the point is, over here we're doing derivatives, over here we're doing integrals, or we're anti-deriving, and so is there some way that we can make a pattern with this? Well, the answer is yes, of course there is. So let's see if we can figure it out. So let's see if we can do this a better way. So once again, I'm going to write down what u is. So u is x squared, and our dv is everything else. It's going to be e to the x dx. So what I'm going to do now is I'm going to make a table. So I'm going to write u on the left side of the table, and I'm going to write dv on the right side of the table. So I'm going to write my u over here as x squared, and my dv over here is e to the x. I don't worry about the dx, because I'm just going to write e to the x there. So what I'm going to do now is I'm going to derive on the left side. So I'm basically going to get these values, this x squared, 2x, and the 2. And you're going to keep going until you get 0. Okay, so I'm deriving over here. I'm taking derivatives. So I'm going to go x squared, I'm going to have a 2x, and then I'm going to have a 2, and then I'm going to have a 0, right? Because the derivative of a constant is 0. If you kept going, you would just get zeros for the rest of the time, right? Now over here, I'm going to integrate. Now e to the x is a nice choice for this, because when I integrate e to the x, I just get e to the x over and over again. E to the x and e to the x. So now, this is where the power of this comes into play. Notice in integration by parts, uv minus integral v du. Nowhere do you use dv, right? uv minus integral v du. So if I think about the first one, the v value is really here, right? Because this is my dv up here, so my v value is really here. So uv, so I'm going to draw an arrow here. So that's u times v, right? So that's my first thing, is x squared e to the x. You'll notice over here, that's the first part that I have here. So x squared e to the x, that's my first piece. And then what happens next is when I bring in this integration by parts the second time, the 2, which is my next derivative, that 2x ends up being multiplied by e to the x, which is the next v. So I'm going to draw an arrow here. And draw an arrow here. You just kind of have these parallel arrows coming down. If I could draw better, they'd be parallel. Okay? And then the rest of them are all going to be 0. Okay? So I'm getting all my terms here. So I integrate on the right, derive on the left, and I'm getting all my terms. So I have x squared e to the x. And then I have a 2x e to the x. And then I have a 2 e to the x. 2 e to the x. And the only thing left to deal with is what are the signs in between? Well, look at what happens with the signs. Positive, negative, positive. Let's see why that happens. In integration by parts, we subtract, right? We do uv minus integral v du. But the second time we do it, we're subtracting the entire integration by parts. So the two negatives are going to cancel out to a positive. And if we did it a third time, you'd have 3 negatives, so it'd be a negative. So all we do here is we alternate signs. So I'm going to put a positive here. Always start with positive, then negative, then positive. So we have a positive x squared e to the x. Then we have a negative 2x e to the x. Then a positive 2 e to the x. And then at the end, don't forget your plus c. And that's all there is to the table method. How much better is it to do this than have to keep track of, gosh, all these integrals and to do u's every time? It's just a huge pain, right? So let's see if we can do that with another one. So the question is, does that always work? Well, yes, as long as you have a polynomial that's eventually going to go to 0. That's the key, is that so like on the cyclic ones, like e to the x sine x, if you do u as e to the x, you're never going to get a 0. If you do u as sine x, you're never going to get a 0. It really has to be a polynomial. At some point, you have to have a derivative that's going to turn into 0. So let's try it with this one. So we're going to have u and dv. Okay, so my u is x cubed, so I'm going to do this until I get to 0. So I have 3x squared. And then I have 6x, and then I have 6, and then I have 0. So there's all my terms. So that's how many lines I'm going to have in my table. So dv here is going to be sine x dx. Don't worry about the dx, right, because we're doing shorthand here. Now, this is where a lot of people make a mistake, because they see this sine x, and they just want to start doing derivatives. But what are we doing on the right here? You're integrating dv, right, because I want to get a v value. So the antiderivative of sine is negative cosine x. Right? Because the derivative of cosine gives me negative sine, so I need that negative there to cancel it out. So the antiderivative of negative cosine is negative sine x. Antiderivative of negative sine x is positive cosine x, and the antiderivative of positive cosine x is sine x. There we go. Now we make our lines. And we put in our signs, positive, negative, positive, negative. Now this one's a little bit more interesting because we have some negatives in our dv's. So we have to be careful about how we approach this. So let's see here. We're going to have, this is a positive. That means that whatever signs are here stick around. So I'm going to have negative x cubed cosine x. And then we're going to have 2 negatives. So that makes a positive 3x squared sine x. Now we have a positive again. So notice they aren't going to alternate this time because we have weird things going on with the signs here. 6x cosine x. And then minus 6 sine x. And then, of course, plus c at the end. Now, if you want a little exercise, and it doesn't really take that long, and it's kind of cool, take the derivative of this. Take the derivative of this. What should you get? You should get x cubed sine x. Everything else should go away. It doesn't take too long. You have to do, what, 1, 2, 3 product rules. But it's not too bad, and it's kind of cool to see everything cancel out. So a little bit of a challenge there. Give it a shot. All right, let's try another one. So here we have a more exciting one, I guess. So we have x squared minus 5x e to the x dx. So let's see if I have a... Oh, I didn't put one in with a... Whatever. It's okay. So we have x squared minus 5x e to the x dx. So... this guy right here is a polynomial. If we take the derivative over and over again, it will eventually turn into 0. So this should work. Okay, so we have our u and we have our dv. So u is going to be x squared minus 5x. Then the derivative of that is 2x minus 5. Derivative of that is just 2, and the derivative of that is 0. We have e to the x over here, and if we integrate that, we're just going to have e to the x all the way down. E to the x. arrows, positive, negative, positive. Always start with positive. So, answer, x squared minus 5x e to the x minus 2x minus 5 e to the x plus 2 e to the x plus c. There you go. Problem that you should take like 10 minutes takes like 30 seconds now. So what I was saying before that I was kind of looking for is I was seeing if I had a problem like this. Let's just put one in. Let's do x squared. Let's do e to the 2x dx. So I wanted to have something that had like a multiplier in here. So now I'm going to do the same thing, u and dv. So u x squared, 2x, 2, and 0. dv e to the 2x. Now when you integrate here, think about this, right? I'm looking for an antiderivative. So there'll be an e to the 2x for sure. And then I have to make that 2 go away when it comes to the front. So I'd have a 1/2. Then we would have a e to the 2x, and then I would have a 1/4, right? Because the 2 comes out here, I need it to cancel out with 1, 2, and we have a 1/2 left. And then I would have 1/8 e to the 2x. So I wanted to show this because once you see the pattern, it's easy to see what's happening, but just be careful you don't get into the wrong pattern. A lot of people would say 2e to the 2x, 4e to the 2x, 8e to the 2x, but we're anti-deriving here, so it's going to keep getting more fractions. Okay, and then of course you do your arrows and the signs, but I'm not going to do that part. So plus, negative, plus, well, why not? I'm here. So we would have x squared over 2 e to the 2x minus, so 2x over 4, that would be x over 2, right, e to the 2x. And then plus, let's see, 2/8 is 1/4, e to the 2x, and then of course plus c. All right. Couldn't leave that unsolved. Had to do it. All right, so let's try one with a simple definite integral. So seeing something this simple, you might be tempted just to go straight to integration by parts, and it's really not that bad, right? U is x, du is dx, dv is sine x dx, and then v would be negative cosine x. So you could just go with this with regular integration by parts, but anytime you have a polynomial here, you can use the table. So if I do du and, u and dv. So u is x, dv is sine x. So we have 1 and then 0. Antiderivative of sine x is negative cosine x. And then we have negative sine x. So arrows, plus, minus. It's simple, it's short, but the table is kind of just a nice way to make sure that you don't make mistakes. So let's see here. Our antiderivative is going to be negative x cosine x. If I had written that better, it's cosine. Okay, and then plus, because we have two negatives here, so plus sine x, and then plus c. Now, if we're doing this as a definite integral, don't need the c, and we just evaluate it from 0 to pi. So we plug in pi, then we plug in 0. So we plug in pi, we have negative pi cosine of pi plus sine of pi. Okay, that's the first part. Then we subtract 0 plugged into the antiderivative. So we have 0 cosine 0 plus sine 0. So let's see, we have negative pi cosine pi. Cosine of pi is negative 1. So this is negative pi times negative 1. Sine of pi is 0. Minus this is 0, and this is also 0. So we have minus 0, right, because it negative distributes. So negative pi times negative 1 is just pi. Cool. So table method makes your life a little easier. Remember, when you're doing limits for integration by parts, doesn't matter about the substitution. You can just plug them directly into the antiderivative. So I believe that's all I've got for you guys. Love you guys. That's why I'm here. Have a great day. Hope you've enjoyed integration by parts.